granted to Professor Ron Chen. Professor Ron Chen is very well known. I think there is no much need to introduce him. Anyways, I will give some glimpses of who he is for those who still do not know. He's editor of International Journal of Vocation and Chaos. The journal was founded by Leon Chua, but since a few years, he is the editor-in-chief. And I should say that after his editor-in-chief, the journal has increased a lot impact factor, now more than 2, right? He has been director of Nonlinear Dynamics Center in City University of Hong Kong since year 2000. Previously, he was professor in Houston and in Rice University in Texas. And he's foreign member of Academy of Europe. He's also member of other academies. And his work in, he has handled also very relevant positions in IEEE. It's one of the most prestigious electronic engineering communities in the world. And okay, his work on nonlinear dynamics, control of chaos, complex networks, are very well recognized worldwide. And also I would like to emphasize that he has contributed strongly to the development of science in China since he has been working in Hong Kong. So please.
Thank you, Chairman. Good morning. Thank you for coming to my talk. My talk is short, so timing is okay for lunch. I will present a talk on a small topic for several reasons. First, the topic is quite new. It's still ongoing. So by the end of my talk, you will see that even you can continue to do many things. Second, it's quite simple. So all of you can understand and follow, including the students. I noticed that there are many students here. No problem to follow my talk. And the third, I hope that you'll find the topic interesting. So the top titles here, you'll see all the keywords. First of all, I'm going to talk about chaos. That's a common interest here. Second, I talk about linear systems. For quite a long time earlier, people believe that chaos only appear in nonlinear systems. That was, generally speaking, was correct and true. But in the past 10-some years, people gradually find out that under certain conditions, chaos could exist in some kind of linear systems. And today, I talk about a new situation where we connect this to weak topology. This is something new. This is a joint work with my former student, C.S.Hsu. He was my student more than 10 years ago. He could be online today. So we worked together in the last couple of years and developed this result. He is a professor now in Shandong University, Weihai. Okay, it's stuck for a little bit. Okay, thank you. As you can see that I will talk about continuous time systems as well as discrete time systems. I will spend a little bit more time on the continuous time setting. So I will talk about the flows, namely solution orbits of linear systems. Basically, in Euclidean space today, all contents results that I talk about today can be extended to Hilbert space without any problem, but I will not go that far. And then I will talk about discrete time. So basically, the mapping, you get time series. So everything is linear in finite dimensional space, except that I will introduce a weak topology into it. So that is today's topic. Now, a little history. So chaos can occur in linear systems was observed as early as 80s, so quite some years ago. If the system, the linear system, is infinite dimensional. So, for example, delay systems, very simple situation, but not all under certain conditions. You can find chaos there. This is the first report. I show you a couple of references here, but I need to make it clear that I'm not doing survey today. So if I miss your contribution, so I apologize for that. I just randomly pick a few that I know quite well and put it there. Give you some information that yes, some people study this topic and there are publications about it. All right. So the second part is PDE. So 20 years ago, I also worked on that linear PDE. However, you need certain nonlinearity where on the boundary. So you see the wave propagate from one boundary to another boundary and bounce back and forth. If the boundary condition is suitably designed, you can generate chaos from there. So the first reference on this PDE, the first author, Chen, is not me. So the Chinese name is easy to confuse. That is Guanrong, professor in Texas A&M, a long-time partner and friends. My name is in the middle, so I put an R there to distinguish from Guanrong. So that, and after that, why I did not continue to work on PDE. Now, not only that, there are more. Chaos has different definitions. So everybody knows Lawrence, you know Lee and York, Devaney. Actually more. It really depends on the definition. Under this definition is chaotic, on the other maybe not. So if it's in the sense of Cato, you could find chaos from linear systems. And here's at least one report there. Or in the sense of Devaney. Now in quantum mechanics, some of you working on that, you already know. Even linear situation, you find chaos from there. So that is a background. In other words, chaos in linear systems is not new. So what is new today? I talk about this weak topology. So I highlight it. From the literature survey I show you, and nobody talk about topology, right? So that is something different. All right. So a few notations. First of all, I use a capital H for the basic space that I'm working on today. It could be general vector space. I said that it could be a Hilbert space, but keep in mind today, just a Euclidean space, just a capital R to the N. That's it. So all rotations and series, right, would be simple, very easy to understand. Then you know, even you can extend it to infinite dimensional. And then the second thing is that we need to use a semi-norm. Semi-norm is not new, of course, but we use it here. Then semi-norm differs from norm in the sense that a semi-norm equals 0 is not necessarily meaning that the argument or the variable is 0. So a non-zero variable, its semi-norm could be 0. Now, why this is useful later on? I'll give you some idea first. So when you have a trajectory, for example, non-zero, but if you look at the norm, then of course, when the norm is zero, this trajectory hit the zero, becomes zero. But if a semi-norm is zero, the curve can be non-zero. And then when you use a semi-norm applied to a non-zero curve, and through the motions, from time to time, it will become zero. I mean, the semi-norm could become zero, but the curve is still up there, which is a non-zero. And then a non-zero curve or time sequence will give you what? It will give you a new piecewise curve or piecewise sequence, whereas sometimes it's a non-zero, sometimes it's zero. That could help you to introduce chaotic behavior. Otherwise, the continuous signal from a linear system could not be chaotic. So that is the whole story behind the scene. Now, how to apply this semi-norm to our framework? Then we look at the dual space. Now you have an X space, right? And then the X star, you put all continuous linear, continuous functionals over there. So it's kind of an operator. You put it there, and then you form another space. We know that from very basic functional analysis. We call that dual space. So if you apply the operator in the dual space to an element in the original space, and then you get a real number. And you can use this real number to define a norm, to do calculation like that. So we will introduce this dual space capital X star, and then I use a rotation, the small z star. Now in finite dimensional case, this functional, basically it's just inner product. Then we can, later on, we will from time to time write an inner product that's easy to see, and you know how to do operation. Now, inner product could be negative, and then we put an absolute value there to make sure that I can use it as a norm or semi-norm. Yes. Or there are just a real line, real number. That's a what we call real value functional. And so functional, yeah, yes. So it's an operator map capture element to a real number. So this R is just a regular R, the real line. Okay, more or less I get ready. So a few notations here. The important thing is the semi-norm. Now I can move on. I need one more concept from calculus. Everyone know, and you learned a long time ago, the limb shoop and the limb inf. So I draw a picture there. I think it's good from Vicky. So limb shoop it's a supremum of the limit of a process or sequence or orbit. So you see that this limb shoop and limb if really is very useful for us to study chaos. You know why? So simple. If you require the limb inf to be zero or with a lower bound anywhere, with limb shoop to be positive or anywhere up there is finite, then the curve inside there would not be convergent because you have, if it's going down and then sometimes you need to go up because you have a limb shoop up there. If we go up and sometimes you need to go down because you have a limb inf down there. So it will not be convergent. It will not be divergent because you have a limit, upper bound, lower bound. It will not go to positive infinity, it will not go to negative infinity. So it will not diverge. And because the shoop is a asymptotic approaching process, so you will not get an exactly periodic motion here. It will be kind of like periodic, but certainly from a mathematical point of view, it will not be exactly periodic. Now, if you exclude these three possibilities, so what's the behavior? It's like a random line. right? So that give you a chance to look for chaos from there. So this Lim-Fu is the major tool for us to use later on. Oh, I have not yet. I have not yet get to chaos. I said that you exclude these three possibilities, then you have a chance to find chaos from the rest, because chaos would not be in the convergent case, right? Divergent case. Yes, good. Okay. Now I define chaos, and not me actually. Lee and York, very smart. They capture the very nature of chaos from what I described. Also from the question from Bontis, Professor Bontis. Now, at the top, I copy just a general formula from ODE from your textbook. Now you have ODE in general is a nonlinear function on the right hand side. And today, later on, I will change it to be just a matrix. I look into only the linear case. So it's an initial value problem. And then we use a rotation. This phi or phi. It's just a rotation for convenience. Use it to describe the solution. Now, any 2 points, we call that a pair, right? A pair of points. Now, these 2 points, if we certify the following 2 conditions, the Lim-Hsu is positive. The Lim-in is 0. That's what I emphasize. If so, then we define that this flow, this phi, this orbit or curve, whatever you call it, it's a Lee and York pair. It's a pair in the sense of Lee and York. Now, this is strong. In what sense? You see, I highlight the all in green color for all elements in the dual space for all. And then we call this a strong. At the very beginning, I put a parenthesis, strong, in the strong sense of Lee and York. It's they appear. So they define it, they emphasize on these 2 limits. And then, of course, for comparison, before I move on, I compare this. You see the next page, I change the all to be 1. So if there are 1 or maybe several, but not all, then we call this a weak at the beginning, weak sense of a Lie pair. Now, the topology is always weak today. You don't need to look at the tail of the phrase is weak topology. It's always weak, but at the beginning, it's in strong sense of Lie and York or in the weak sense of Lie and York. That's a different. So later on, the result will come out differently. But of course, you don't have to distinguish it so seriously today within this a few minutes. But I need to make it rigorous here. Okay, move down. Now, if you have a subset of these points, right? These pairs of points there, then if this is you have for 2 such pairs, if they are strong, Lie and York pairs, and then we call this scramble set. Just give a name. Today I don't use this name, but I need to prepare for this and make it rigorous. And if this scramble set is uncountable, in particular, this is a case of chaos. If it's a finite, it won't give you much. So if it's uncountable, and then this flow will be called, in the strong sense of Lie and York, chaotic within this weak topology framework. So the topology, in summary, is introduced to the original space capital X from the dual space capital X star, and using that to define a semi-norm and use a semi-norm to apply to the original space, and that in that sense we introduce a new topology to it defined by the semi-norm. So we call that weak topology. So strong Vitus, it's just a concept of relative description, and in different situations, it has different meanings. So today in my presentation, and that is the meaning of a weak topology. Okay, important thing is these two limits, the lim sup and lim in. So I said that if there's only one or maybe several, but not all, we call the weak sense of Lee and York. Okay, now let's come back to the initial value problem. The same, I copied it up there. Now for linear systems, now you see that I changed the capital F to be capital A. It's a matrix. Then you know that for linear systems, what about the solution? It's either stable or unstable or periodic. That's all. No more, right? Correct. This our undergraduate ODE course contents. And then down here, I will just remind you, actually you know that quite well. If A has all different real eigenvalues, and then the flow would not be weakly linear chaotic in weak topology we introduced today, would not happen. Why? That's easy to verify. Because you have all eigenvalues, so you just put it into the solution formula. So students know that for linear ODE, the solution formulas can be expressed by the eigenvalues, right? So you compare the difference of two flows, and then you calculate the semi-norm. And then you, according to definition, semi-norm is the absolute value of the inner product. And by definition of inner product, you put it into the summation. That everything come out. We can use this as a homework exercise for ODE course. And then you know that the limit is either 0 or finite or infinity, and no others. So will not be chaotic in any sense. Okay, this is the first situation, but is this true for all situations? No. I show you one case. There are several cases, and this case is easier to say, easier to describe, and easier to understand. Just a very special case, but I show you, then you can verify that this case really give you the New York chaos in the weak topology. Okay, the example is the following. You have two blocks, Jordan blocks, the J and the complex conjugate. And then you put all the eigenvalues there. Small n could be 1, right? And then you put the complex conjugate on another block. So you have a block diagonal matrix with all eigenvalues and the multiplicity. Okay, you put it there. Now here's a conclusion that you can prove, you can verify. Now the first one, if the real part is negative, then you know that you have a stable system, or trajectory converge to somewhere to 0 for linear system in general. But there certainly would not be possible for you to define it to be chaotic, including in the weak topology case. However, now if the real eigenvalue is non-negative, you have a chance. Because it could diverge. But we said that we have a lim sup to bound it back. So if this situation really have a lim sup, then it will not diverge. A lim inf also, it will not diverge to negative infinity. Then you have a chance. So let's verify to see if this is really the situation. And then in order to do this, not just a verification for the lim sup and lim in. Yeah, so student can do it. Just spend some time. Okay. Now, in order to do this, I need just to simplify some notation. Otherwise, you can matrix and matrix and matrix. That's horrible. Now I put all the eigenvalues on one side, on the left, and all those the multiplicity on the right side, because what is important is eigenvalue. So I can write the exponential matrix e to the t times this is Jordan and into a form. The capital gamma is a matrix that includes everything else but the eigenvalues. So I separate the eigenvalues, in other words. And then the eigenvalues could be complex, so I write it in alpha and beta. So it's just a reformulation. I put it in this form. And then I want to verify the limit, right? The lim sup and the limit. So in order to do so, I need to do some calculation. Now, again, I just want to simplify the notation. Otherwise, it's horrible. So from the top down, you'll see that I introduced some shorthand notation, S1, S2, S3, S4, and so on, just for convenience of notation, nothing else. So you can reformulate it, and then finally, at the bottom, you'll see that your exponential matrix can be expand in terms of this S1, S2, and so on. And then it's easy to do calculation or proof. Now, in this case, you have a formula, and then now you verify it. So first of all, the solution is given by the formula up at the top. The for linear systems, right? That is a solution. And then we put it into the semi-norm. We compare two trajectories to see how they separate or how they merge together. We want to understand that. And so you calculate the difference of the two trajectory, and then you calculate the semi-norm. So the measure is in the semi-norm again. And then you, by definition, is in product, and then you can do it just a simple calculation, a little bit messy, but it's just straightforward. And then you calculate, and then it's still too long of the formula. So I let M1 be that mass and M2 be another mass, and put them together. Then finally, you see the semi-norm equals to the right-hand side at the bottom. That makes it quite simple. And then you can go ahead and verify it because now you know everything. Then these two limits, either 1 or 0 or a constant for that part of the solution, not the whole solution. So just to remind you, let me go back. It's M1 and M2 only, but you still have a cosine, you still have the eigenvalue out there. And the eigenvalue is important. Okay, then now you go ahead and verify the limit. And then when real part is negative, so again, you know, it must be stable. Indeed, that's correct. And they get together. The two trajectories gradually get together. And then when the real part is not negative, then you calculate in our situation when you have a Jordan and the complex conjugate of Jordan. In this situation, the lim sup is positive. It's a finite number. You don't care what number it is. It's not infinity. It's not 0. So it's a positive. But that verifies Lee and York's definition. So in this sense of Lee and York, it's chaotic. All right. So this case is easy to solve. Not that lengthy and not that complicated. No other things involved. Okay. That gives you some idea about the study and what kind of result we are going to get. It simply is just in some cases of this linear system with weak topology, it could be chaotic in the sense of Lee and York. Now I show you one more simple example. You see this like harmonic oscillator. Now for linear case, if you don't apply weak topology, namely if you don't care about semi-norm, you use the regular norm, it is either convergent or divergent or periodic. For this case, it's periodic, right? So we have a spiral curve. Now the semi-norm, when you apply it once more, physical, clearly understand how come the semi-norm can make it chaotic. The semi-norm will make non-zero curve become 0 because it's semi. And so when you have a continuous curve, from time to time, the norm make a small piece of that become zero. You have a piecewise continuous function. That give you a chance to have chaos. So it depends on the setting. The setting give you the solution. Depending on that solution, and this piecewise curve could exactly satisfy the definition of Lee and York. That's the whole story. So this is can be verified. Now I talk about real eigenvalues, right? So what about complex conjugate eigenvalues? Yes, here the proof or verification is about the same. I don't repeat. So for complex conjugate case, so if they have a non-negative real part, that's necessary, right? I just show you. Even real case, the complex case could be real. The imaginary part is zero, then you get a real eigenvalue. So this is true also for complex eigenvalue case. There's no problem. Now, I think because I know I just have that 40 minutes or so. So I stop here for the continuous time setting. You get the main idea. And then I extended to maps to discrete case. Then of course you say, I can imagine how to do it. Yes, exactly nothing new here. But let me just formally present to you. We consider a map capital T, and then the map, iterate the map, you get a time sequence, right? You get a sequence of solution in the solution, x, tx, t square x, and so on. And then the definition is similar. You look at the lim sup, which should be positive, meaning a positive number, not infinity. And lim in should be zero. Now these two can be shifted up and down, but just follow Lee and York definition. That's easier. Don't look at the lower bound becomes a negative case. It's not necessary. The same thing. Okay, everything is the same. I don't repeat. Then what's the result? Is there anything different? Yes and no. In principle, in idea, no difference. But technically, yes. This case, you know that. For example, logistic just one-dimensional can generate chaos. Right? For continuous cases, it's not possible. Okay. Here for discrete case, for the capital T, let me show you a special case first. This special case is two-dimensional. And then later on, of course, you can extend it to, I will, higher dimensional. Now, two-dimensional case is easy to follow, to understand. Let's say case one. Case one, there are only two real eigenvalues, lambda 1 and lambda 2. And these two are the same but opposite in size. So the absolute values are the same. The magnitudes are the same, but the size is important. Saddle point. Yeah, but it's a real. Yes, but there's a real saddle point, not complex. I will come to complex next. This is case one. Okay, good. Now, and in this case, I can even show you, I can construct a scramble set. Now here, you see, that I can find one, I highlight that one continuous functional in the capital X star space. I can find one. Of course, there are maybe more. Which one? I give you the construction here. So this point is not zero. And then I can put it in the denominator, right? And then I can construct that K is just a real number. And this set is a scramble set. You can verify this. And then we not only verify this as the situation that satisfies Lee and York definition, but also I give you a very precise construction. You can see. I'm sure you can construct more, but I show you one. Okay. Now, second case, that's your question. Now, if the eigenvalue could be complex, now I require, this is a necessary condition. They must be complex conjugate in order to generate chaos in my setting, okay? So For real case, the size should be opposite. For complex case, they should be complex conjugate. Now, if so, I also construct a scramble set for you, even simpler, so no problem. And then recently, there's one more report. So here, the second order, Professor Yang, he was my postdoc like 20 years ago. I did not participate into this particular work. And the first author is his PhD student. So I give them the paper to read, only 2 papers that summarize what I present to you today, published just this year, and one last year, one this year. And then they read it and study it, and they come up with the following. They look at the map. So they only look at the discrete situation. So I said that this is open-ended research. You can think about the continuous case. Now for them, they look at the discrete case, look at the maps, and then they prove. Now one-dimensional case, of course, are not possible, even in the weak topology. So they conclude this. And then when dimension is larger than or equal to 2, now there are different situations. The first situation, if the 2x2 matrix, now if n is 2. Now if n is bigger than 2, and then at least you have 2 real eigenvalues. And these 2 real eigenvalues here, they must be, you see, the size must be opposite. And the magnitude must be bigger than or equal to 1. Because of this is a discrete case. So it's outside or on the boundary of the unit circle. Now, the good thing is that I show you already, but that's only necessary. They said, oh, this is also sufficient. That is good. So they come up with if and only if. Yeah, opposite in the sense, no, in the sense that they have the same magnitude, but opposite sign. I'm 5, you're -5. You're -3, I'm 3, in that sense. But when I write it in English, is there any better description? That's what I mean, right? Opposite. Okay. Maybe maybe it's not very clear. The opposite. What do you mean by opposite? Yeah, one up, one down is also opposite. Thank you. Okay. So when I give a presentation, it's easy to describe. But when people read the paper, maybe they feel confused. Yeah, thank you. Okay. Now this is the case would be equal to 2. Now going up, dimension higher, the dimension is at least 3, and then they look at 1 real eigenvalue, 1 pair of complex conjugate. And this is also necessary and sufficient. So their contribution, I think they get the same idea from us, but they fill the gap. They said, oh, it can go both ways. Xu and I did not think about necessary and sufficient conditions. Just say, oh, this is generally chaos. We were excited. Oh, this is good. Okay. See that they summarize it here. If capital that matrix A is a higher dimensional, it has a real and complex eigenvalues, and then necessary and sufficient condition is either 1 or 2. So this is or, not and, either one. If it has 1 pair of real opposite eigenvalues, or they have 1 pair of complex conjugate eigenvalues, that's necessary and that's enough. That's sufficient. So quite a beautiful result, actually. I did not list the reference here, but just in case you need, contact me. So far, there are only 3 papers on this topic. 2 with my student Zhang with me, and 1, the last one. Okay, the last one just published last month. Okay, to summarize it, I think I would say that I don't have to summarize. You know that. Oh, this you haven't done it. There are many things you can consider, right? So I welcome students to spend some time to think about it. So in case you need reference, contact me. Thank you very much to us stop here.
Thank you for your nice talk. Now it's time for some questions, comments. Any question or comments? Okay.
Can you visualize this? This is a very interesting and beautiful mathematical construction. Can you visualize any type of physical system that might be described by this equation?
Yeah, that's a good question. And actually, I mentioned it. I said that you look at a harmonic oscillator. I show you the two-dimensional special example, alpha on one diagonal, beta and minus beta on another diagonal. Yeah, you remember the example? And then the solution is a spiral, long, a spiral curve. No, it's a periodic. It's fine. Now the measure is that I apply the semi-norm to it. Let's say the semi-norm project to the x-axis a certain interval there is zero. So when the motion moves there, you get a zero number. Not the curve, but the semi-norm of the curve. Yeah, and the limit is about the semi-norm. The semi-norm go to the upper limit, lower limit, because the limit give you, the norm give you a real number. You can talk about the limit. The curve is just an element. It could be anything. You cannot talk about limit. Right. So when cut off it, give you zero. So your curve, when you try to plot the curve, what do you get? Originally, without applying the norm, you just get a continuous curve, maybe a sine wave. But when you apply the norm and you look at the norm suddenly give you zero somewhere, and then it come back, suddenly give you zero somewhere, you come back, and suddenly give you zero. So you have a piecewise non-zero curve and with piecewise zero, zero in the gap. And that gives you a chance to have chaos. Otherwise, that's just an oscillation. Yeah. That should visualize it, right? Yeah, that visualize the reason behind the result. Thank you.
Any more questions? No question, no comments?
It's simple.
Okay. Thanks, the speaker again.
Thank you, thank you, thank you all. Thank you all for listening. I can also give you a PowerPoint. Just contact me.